For the complex analysis, we should know about the two types of variable. One is real variable, another is the complex variable. So any complex number, if we talk about the complex number, then complex number is made with two parts. I say x plus iota y. This is called one of complex variable. Any complex variable z is equal to x plus iota y, where this x and y both are real. This iota, this is called iota, you already studied. Iota is complex. Iota is square, always iota square gives minus of one value. So this is called complex number. So if z is any complex variable where x and y is real, then z is given by x plus iota y. Next, if I define a function on this variable, function of a complex variable. If I want to derive this function of complex variable, what is the function of complex variable? Let us consider s, capital S. Let us consider a capital S is a set of all complex number, like z is x plus iota y, one complex number. Second, we can say w is another complex number. I can say w equal to x1 plus iota y1 and so more. So S is the set of all complex number. For each of z in S is a complex number w where is mapping occurs. For example, what is mapping? Now, if we talk about the mapping in simple real number, if we have two sets, I say there is x and y element, there is 1 and 2 element, then there is a function defined that x related with 1 and y related with 2. We can say f of x equal to 1. Here the function is f of y equal to 2. So this is called mapping, simple, and f is called function for any real variable. Similarly, here we define the function of complex variable. So if S is our set of all complex variable, then we can say for every value of z inside the S, w is the number which is also present in S given the mapping for z to w. Then we can say function of f z is equal to w, means mapping from z to w, define this function like that. So fz equal to w is our complex function which is given by u x comma y plus iota v x comma y. U and v are any two real variable function. Then the set S is the called domain for this given function. Now if we talk in polar coordinate, how we write in polar coordinate? We can say w equal to f of r e to the power iota theta. So this is polar coordinate, and we can write in u and v form. U r comma theta plus I v of r comma theta. Clear? So this is the function in Cartesian coordinate, this function in polar form we can define. So for example, similarly, if we talk about the example, very simple, if I say fz equal to z square. Clear? So what is z is x, z is x plus iota y. So I can say this is x plus iota y whole square. So when I open this, it becomes x square plus iota square y square. Iota square is minus 1, so it gives x square minus y square plus 2 iota x y. So what is my u? This is u of x comma y part, and 2 iota remove 2 of x y is v of x comma y function. You understand? This is the small example for my function of complex variable. See this, inside this window we can see fz is equal to g square, x is equal to z is equal to x plus iota y whole square. When we open, then our function fz equal to w is equal to u plus comma xy plus iota. What is uxy? Uxy is x square minus y square. What is vxy? Is 2xy. Clear? So this is all about the function of complex variable. Single valued and multiple valued function. Single and multiple valued function. Valued function. So what is single valued? If I say, if I have a one domain here, another domain here, if my variable is z, its mapping with w, and defined function is f, fz equal to w, then I say for every z, if there is only one single value is present in domain, then that type of function is called single valued function. And what about the multiple value? If multiple valued, I say it is w1 and one more variable w2. I say z is defined with w1 also and w2 also, means for z there are two value or more than one value is called multiple valued function. So for single valued, z always mapping with the other side with the only single element. For multiple value, it consists more than one value. For example, if we can say fz equal to square root of z. Square root of z means x plus iota y. So square root is given the value of plus minus, means it gives the value of plus minus x plus iota y, or we can say plus minus and square root of r e to the power iota theta by 2 in polar. So for single value of z, here it gives two value of function, one in positive aspect and second is negative aspect. So this type of function, this is one simple example for multiple valued function. Next, when we describe the function, we need for complex analysis, or before we describe the analytic function, we should know about the some more result. First is the Euler theorem. What is our Euler theorem? Euler theorem is e to the power iota z is equal to cos of z plus iota sine of z. So this is Euler. And then next is the cos de Moivre's theorem. What is de Moivre's? If we have trigonometrical function cos plus iota sine z whole to the power n. So according to de Moivre's theorem, we should write cos of nz plus iota sine of nz. So this of Euler This because of De Moivre's theorem. So these results we should know because we already previously learned about in complex analysis. So this is next when we talk about the complex analysis, there is very important role of the hyperbolic function. We know if my first hyperbolic function is sine of hyperbolic z, then sine hyperbolic z I should give with e to the power z minus e to the power minus z divided by 2, correct, where cos of hyperbolic z is given by e to the power z plus e to the power minus of z divided by 2. Clear? So these are the hyperbolic functions. Similarly, with the help of sine and cos, we can define all other hyperbolic functions. Next, relation between the circular function and the hyperbolic function. If I have the circular function, for example, if I say sine of iota z, this is my circular function. So sine of iota z is e to the power iz minus e to the power minus iz divided by 2 iota, and cos of iota z is given by e to the power iota z plus e to the power minus iota z divided by 2. So there are relation between these two functions. First one is this hyperbolic, second one is this circular function. Now what is the relation of these function? I can write in the empty box. So now we can talk about the relation. So if I relate it, it will be given by sine of iota z is given by iota sine hyperbolic z. Clear? Similarly, cos of iota z is given by cos hyperbolic z. Cos hyperbolic z. So this is the relation between the circular function and the hyperbolic function. Similarly, we can define for our sec, cosec and tan cot functions. So these are the basics before we start the analytic function. Equation is very important for complex function, or we can say for any analytic function. So what is this Cauchy-Riemannian equation? For this Cauchy-Riemannian equation, we can say the necessary and sufficient condition for the derivative of function w equal to fz equal to u plus iota v. This is any complex function w equal to fz, where fz is u plus iota v, is exist for all value of z in the region R, whatever the given region. So what are these equation or what are these conditions? So for w equal to fz, this function derivative will exist on that region only when we can say del u by del x equal to del v upon del y and del u upon del y equal to minus del v upon del x, or we can say ux equal to vy and uy equal to minus vx. It is the easier way to remember this equation. So these are called the Cauchy-Riemannian equations. If for any function where u and v are the real function of variable x and y, is differentiable at that point or at that region only when these conditions are satisfied. So if we want to check the differentiability, we check this Cauchy-Riemann equation is satisfied. If it is satisfied, then that function will be derivable, differentiable. So what is the differentiation of this function? I can say differentiation is f differentiation of this function is f dash z is given by del u by del x plus iota del v upon del x, or we can say f dash z is also same as del u by del y plus iota del v upon del y of that function is given by this equation either or this equation. Either you can say derivative in respect to x del u by del x plus iota del v by del x, or we can say f dash z is equal to del u by del x plus iota del v by del y. So this is called Cauchy-Riemann equation. This now I will show you Cauchy-Riemann equation in polar form. Then in polar coordinate we know x equal to r cos theta and y equal to r sin theta. This is the transformation from Cartesian to polar coordinate. Hence z equal to x plus iota y. So we can say this is r e to the power iota theta. R e to the power iota theta. So in Cauchy-Riemann equation in polar form we can say del u upon del theta equal to minus r del v upon del r. And second one is del v by del theta equal to r del u by del r. So these are the two equations in polar form. So these are the equation in polar form. For Cartesian we can say ux equal to vy and uy equal to minus vx. But in polar, in r and theta, our equation is del u by del theta equal to minus r del v by del r, and del v by del theta is r del u by del r. Now I can solve some examples how to find out the derivative of any given function. So we go and here we discuss the differentiability of any function. Differentiability we can check only with if Cauchy-Riemann equation is satisfied, then we can say it is differentiable at that point. So for example, if I say if function fz equal to ez, then find the derivative of this function. Question is fz equal to e to the power z. Find the derivative of this function. So e to the power z means e to the power x plus I y, correct? where e to the power iota theta is cos theta plus iota sin theta. So we can say it is e to the power x into e to the power iota y. Now this e to the power iota y we can expand with e to the power iota theta. So e to the power x cos y plus iota sin of y. Now we can separate our function u and v. So here u equal to e to the power x cos y and v is e to the power x sin y. Clear? Now our Cauchy-Riemannian equation ux del u by del x is ux. So ux, when we differentiate partial with respect to x, it gives e to the power x cos y. Derivation of ex is ex. Then uy, differentiation with respect to y is minus dy by dx of cos y is sin y minus of, correct. So it is e to the power x sin of y. Similarly for vx, vx is given by e to the power x sin y, and vy, differentiate v with respect to y, give ex sin y, derivative is cos y. So ex cos of y. Clear? Now we can say ux equal to vy and uy equal to minus vx. It means Cauchy's-Riemannian equations are satisfied here. We can say ux equal to vy and uy equal to minus vx. Cauchy's-Riemannian equation if satisfied, then we can say this function are differentiable. So now we can easily find out the derivative of this function. So now I will find derivative of this function here. What is derivative of this function? Derivative we can give f dash z is equal to del u by del x plus I del v upon del x. Yes, either del u by del x plus I del u v by del x, or we can say del u by del y plus I del v by del y. Now you substitute the value of del u by del x and del v by del y from here. So del u by del x is ex cos y, del v by del x is ex sin y. So we can say this is ex is common cos of y plus I sin of y. So we can say cos theta, cos of I plus I sin of I is iota y. Again this is e to the power x plus I y. So again it becomes e to the power z. So derivative of given function e to the power z is same of e to the power zc. Check. So derivative is also e to the power z. So for any function finding the derivative, first we check either it is satisfy CR equation. If it can satisfy, then we can easily find out the derivative of given function. So that x cube 1 plus iota minus y cube 1 minus iota divide by x square plus y square, where given the condition z is not equal to 0 and f0 value of function at 0 equal to 0, then it is said that is continuous and CR equation satisfy at origin, yet f dash z f dash z does not exist. Is here. So f dash z is always unique. So first we check if either this is satisfy CR equation at origin. If it is satisfy CR equation at origin, then we go for f dash z. So we can start the solution. First of all, we can find out our u and v. So our u, when we find the u, our u is x cube minus y cube upon x square plus y square. See, from here this x cube minus y cube upon x square plus y square, and our v is equal to x cube plus y cube, x cube plus y cube upon x square plus y square. See, x cube, iota part is x cube minus minus plus y cube upon x square. Now we can check that u and v are the rational and finite value at z is not equal to 0. So u and v are continuous for all points where z is not equal to 0. Hence fz is continuous when z equal to 0 point 0. So if we want to find this derivative at point 0, then limit x tends to 0 u x comma 0 minus u 0 0 upon x. When we substitute value of u x comma 0 means y, when y is 0, u x comma 0 is give only x. So u x is equal to limit x tends to 0, it gives x, u 0 0 is 0 by x. Hence x by x gives value 1. So del u by del x is equal to 1. Similarly, we can find del u upon del y. Del u by del y is limit y tends to 0 u 0 comma y minus u 0 0 upon y. Yes, when we substitute these values here, we will see that it gives minus y upon y. Limit y tends to 0 minus y upon y. So it gives the value minus of 1. Similarly, from v we can find out the two other del v by del x and del v by del y. When we derive similar way del v by del y, then del v by del y is coming 1. So that is also we can write it is v of y, and del v upon del x is also 1. So del v of x is also 1, because here both the values of x and y between plus notation. So del u by del x, del v by del y and del v by del x, both partial derivative with respect to x and y at point 0 gives the value plus 1 only. Hence when we check the Cauchy-Riemannian equation. Del u by del x means ux equal to vy. First equation is correct. Second equation is uy equal to minus vx. That's also true. Hence, this function satisfies CR equation at point 0, 0. Now it means it has its derivative. Now if we go for its derivative, then the derivative limit z tends to 0, limit z tends to 0, fz minus f0 upon z. With the help of definition of differentiability, we can find this derivative. Now we put the values of function f0 is already at first give f0 equal to 0. Then when we substitute these values here, limit z tends to 0, we can substitute fz. Here our fz is x cube minus y cube plus iota x is x cube plus y cube upon x square plus y square. This is for fz minus f0. So f0 is 0 into 1 by z. So 1 by z, z is x plus iota y. Clear? So this is our function of fz minus f0 by. Now we can check that this value is the unique solution for f at point 0 or it doesn't exist. When we put z equal to 0 at x equal to y. If x equal to y, then it's also give x equal to 0. Then when we substitute x equal to y in above equation, it will give the value f dash 0 equal to f dash 0 equal to 1 upon 1 plus iota. Iota upon 1 plus iota. When we substitute here x equal to y, x cube minus y cube cancel out. This is x cube, this is also x cube. So if we put x equal to y or either y equal to x, then this is 2x cube iota. This is also 2x square into what it becomes, x plus iota x. So x can taking outside, so this is 2x cube, 2 cancel, x cube cancel, only remaining is iota upon 1 plus iota. Similarly, for another solution, if we put z is equal to 0 at y equal to 0, then now we check at 0 point, if y equal to 0, then it will gives the value, see, y equal to 0, then it gives x cube plus iota x cube, remaining also x into x cube. So it gives the value only 1 plus iota, f dash 0 equal to 1 plus iota. Hence, it doesn't gives the unique solution for 0 point. So f dash 0 does not have unique solution. Hence, f dash z does not exist at 0, 0, or we can say it does not exist at origin. So sometimes it may happen if CR equation can satisfy, but it doesn't have any unique solution for derivative, so it doesn't exist its derivative. Now we talk about the analytic function. Z is said to be analytic only when it is single valued. Fz is said to be analytic when it is single valued function, possesses a unique derivative with respect to z at all points of region R. And one more thing, if a given function satisfies the CR equations, Cauchy-Riemannian equation, then we can say it is continuous and differentiable at given point. Then that function also called analytic function.